Welcome to Teolumen Insights, where we reveal the hidden forces that shape the way you live and show you how to use them to create real transformation and supercharge your health, mindset, and daily life. Here are your hosts, Emma Greenwood and Nathan Sinclair.
Hey everyone, and welcome back to Teolumen Insights. It's amazing to think that some of the most well-known ideas in science can also be some of the most misunderstood.
Yeah.
You know, like Heisenberg's uncertainty principle? I feel like we've all heard of it.
Yeah.
But it's often presented as this like mysterious limit on how much we can know about the universe.
Right.
Like if we try to look too closely, reality gets all blurry or something.
It's definitely a common misconception.
Yeah.
People often think that the uncertainty principle is all about the limitations of our experiments, like the act of observing something is what disrupts it.
Right.
But what if I told you there are theories out there that suggest particles might actually have defined paths, even in the quantum world? We call these trajectory-containing quantum theories, or TCQTs.
Okay, now that is intriguing. So on the one hand, we have this very famous principle saying we can't know everything about a particle.
Right.
But on the other hand, we have these TCQTs suggesting particles might actually have these clear paths that we just can't perfectly pin down. So how do we even begin to reconcile these seemingly contradictory ideas?
Well, a good place to start would be to take a look back at the history of the uncertainty principle.
Okay.
Maybe start with Heisenberg's 1927 paper where he first introduced the idea.
Okay, so let's unpack that a little bit. Heisenberg was a big proponent of operationalism, right? The idea that we should define physical concepts based on how we measure them.
Exactly. And in his paper, he uses this approach to argue against the very concept of particle trajectories. He uses this example of trying to measure an electron's path in a hydrogen atom. And he argues that if you use even a single photon to measure the electron's position, that photon would have so much energy that it would just knock the electron right out of the atom.
So it's like trying to figure out where a soap bubble is by poking it with a needle. You're just going to destroy what you're trying to observe.
A very apt analogy. And so Heisenberg concluded that since you can't measure the electron's path without disrupting it, the concept of a trajectory is meaningless in that context.
I'm starting to see his logic. But it also feels a bit circular, doesn't it? It feels like he's defining the problem in a way that guarantees there's no solution.
You've hit on a key point, and this is where things get really interesting. Even though his paper is famous for introducing the uncertainty principle, his argument against trajectories there didn't actually rely on it.
Wait, what? So the uncertainty principle wasn't even part of his initial argument against particle path?
Not in that specific paper, no. His issue wasn't actually with the simultaneous measurement of position and momentum, which is what the uncertainty principle is all about.
Okay.
It was all about the disruptive nature of the measurement itself in that particular example with the hydrogen atom.
So where does the uncertainty principle come into play in all of this? When did Heisenberg start using it to argue against trajectories?
Well, for that, we need to fast forward a couple of years to his 1929 Chicago lectures.
So Heisenberg kind of changed his tune a little bit in these later lectures.
Yeah, a bit. In the lectures, he really starts focusing on the uncertainty principle as the main reason we shouldn't assume particles have trajectories. He argues that since the uncertainty principle limits how precisely we can verify those trajectories, it's kind of unnecessary to include them in our picture of quantum mechanics.
I see where he's coming from. But couldn't you argue that just because we can't prove something exists doesn't mean it doesn't? Like absence of evidence isn't always evidence of absence, right?
That's a very valid point. And in fact, Heisenberg's argument in these lectures actually rests on a pretty shaky foundation.
Oh, what was wrong with his logic?
He makes this very specific assumption about the relationship between a particle's momentum and its wave function. And it turns out his model is just incorrect.
So his whole argument was based on a flawed premise.
Essentially, yes. In fact, his model wouldn't even reproduce some well-established rules in quantum mechanics, like the Born rule, for example.
So even brilliant physicists like Heisenberg can get things wrong.
Yeah.
It's kind of reassuring in a way.
Absolutely. Science is a process of constant refinement, you know?
Yeah.
And even the greatest minds make mistakes. What matters is that we learn from those mistakes.
Right.
And keep pushing for a deeper understanding.
Okay, I completely agree. But if Heisenberg's model was wrong, where does that leave us? Are we back to square one with the uncertainty principle and particle trajectories?
Not quite. There's actually a really fascinating twist that makes this whole story even more interesting. Even though Heisenberg's reasoning was flawed, his intuition about the limits of prediction in a world with particle trajectories was, well, kind of right.
Hold on, I need to process this for a second. So he was wrong about why we can't precisely predict trajectories,
Yeah,
but he was still right that we can't predict them.
exactly. And this is where the work on Bohmian mechanics comes in. Remember those TCQTs that we mentioned earlier?
Right.
Well, Bohmian mechanics is a TCQT.
Okay, so Bohmian mechanics says that particles do have trajectories.
Mm-hmm.
But how does that work with the uncertainty principle? If particles have paths, shouldn't we, be able to predict where they're going?
It is a bit counterintuitive, but in Bohmian mechanics, the spread of the wave function after you measure a particle's position is actually limited by how accurately you made that measurement.
Wait, I need to rewind for a sec. So we make a measurement,
Yeah.
and that affects how the wave function, which, describes the particle's probability,
Yeah,
spreads out.
precisely. And because of that, even though particles might have these definite paths, we still can't actually use that knowledge to predict their future position with perfect accuracy. The wave function kind of gets in the way, so to speak.
Okay, so that is really interesting. So even if there are trajectories, the uncertainty principle still holds in a way because of this wave function spreading.
Yeah.
So Heisenberg was right about the limitations,
Mm.
just not for the reasons he thought.
You got it. It just highlights how even a flawed argument can sometimes lead to deeper insights.
This is kind of blowing my mind. But I have to ask, if we can't predict things precisely even with trajectories, wouldn't it be simpler to just stick with a theory that doesn't even bother with them in the first place? Why even complicate things?
I mean, that's a valid perspective, especially for physicists who are really focused on making predictions.
Right.
But there's actually another twist that might just sway even the most prediction-focused minds.
2 twists in 1 episode. You're spoiling us. What's this new wrinkle?
Well, it turns out that standard quantum theory, the one without trajectories, actually runs into some trouble when it comes to something called arrival time measurements.
Arrival time measurements.
Yeah.
I'm not familiar with that. What are we talking about here?
So imagine you have a particle that's trapped in a box, right?
Okay.
And then you release it, you set up a detector a certain distance away, and wait for the particle to arrive.
Okay.
Now, standard quantum theory actually struggles to give us clear predictions about when exactly that particle will hit the detector.
Wait, are you saying that standard quantum theory just, gives up on predicting arrival times? How's that even possible?
It highlights a really key difference between standard quantum theory and TCQTs. Because TCQTs include the concept of particle trajectories, they actually offer a much more natural and straightforward way to calculate those arrival times.
Wait a minute. Are you saying that TCQTs, despite all this uncertainty and everything, are actually better at predicting certain things than standard quantum theory?
In some cases, yeah.
Wow, I did not see that coming. So even those physicists who prioritize making predictions might actually have to reconsider the value of TCQTs thanks to these pesky arrival time measurements.
You're catching on quickly. And this is exactly why exploring all these different perspectives is so important. It challenges our assumptions about what even makes a good theory,
Yeah.
Sometimes the theory that gives us the most intuitive picture of reality might actually be the one that gives us the most practical tools for specific problems.
This whole discussion is making me wonder if the debate about whether the uncertainty principle is about what we can know versus how the universe actually works is kind of a philosophical question in a way.
That's a really insightful observation, and it speaks to the heart of what makes quantum mechanics so fascinating. There are all these different interpretations, different ways of looking at the same mathematical framework.
Yeah.
And depending on which interpretation you favor, the uncertainty principle can take on these slightly different shades of meaning.
Okay, yeah. I'm definitely getting a sense of that.
Yeah.
But before we wrap up this part of our deep dive, can we go back to Heisenberg's Chicago lectures for a moment?
Yeah.
You mentioned that he had a very specific way of thinking about the wave function.
Yeah, absolutely. He saw the wave function as this representation of our knowledge about a particle rather than something that was inherent to the particle itself. He has this really striking quote in the lectures that sums up his view. He says, if one wants to clarify what is meant by position of an electron, one has to describe an experiment by which the position of an electron can be measured. Otherwise, this statement has no meaning.
So for Heisenberg, the wave function wasn't this objective physical thing.
Right.
It was all about what we as observers could possibly know.
That's how he saw it. And this epistemological view of the wave function was really central to his argument against trajectories, because if the wave function only represents our knowledge and the uncertainty principle limits that knowledge,
Right.
then it follows that we can't meaningfully talk about particles having definite paths.
It all comes back to his operationalist viewpoint.
Yeah.
Define things by how we measure them.
Mm-hmm.
But if our measurements are inherently limited,
Yeah.
then our definitions have to be limited too.
Mhm.
It's very self-consistent, even if it isn't the whole story.
Exactly. And that's why understanding these different interpretations of quantum mechanics is so crucial.
Yeah.
They each offer a unique perspective on the uncertainty principle and what it tells us about the nature of reality itself.
Well, on that note, I think we've reached the end of part 1 of our deep dive. But don't worry, there's plenty more to come. We'll be back soon to explore even more mind-bending ideas about the uncertainty principle, particle trajectories, and the different ways of interpreting the quantum world.
Yeah.
See you soon.
Looking forward to it.
All right.
All right. It's fascinating how even when a scientific idea is based on a flawed premise,
Yeah.
it can still spark these new discoveries and lead to even deeper insights,
Right.
Like Heisenberg's initial rejection of trajectories might have been off the mark,
Yeah.
but it ultimately led to a much richer understanding of the uncertainty principle
Right.
and its implications.
Yeah, it's like stumbling upon a hidden path while you're searching for something else entirely.
Yeah.
You might not find what you were originally looking for,
Right.
but you discover something even more intriguing along the way.
Exactly. And that's the beauty of scientific inquiry,
Yeah.
It's this constant process of exploration where these unexpected twists and turns can lead to really profound breakthroughs.
So we've talked about Heisenberg's view of the wave function as representing our knowledge about a particle.
Right.
But how does that contrast with the view of the wave function in those trajectory-containing theories,
Yeah.
the TCQTs?
That's a great question. You see, for Heisenberg, the wave function was all about epistemology.
Okay.
The study of knowledge. It was
Yeah.
about what we as observers could possibly know about a particle.
Right.
But in a true TCQT, the wave function takes on a much more fundamental role.
Okay.
It's tied to the actual laws of motion,
Okay.
the nomological aspect of the universe,
Right.
not just our limited understanding of it.
So for Heisenberg, the wave function was about what we can know. While in a TCQT, it's about how the universe actually works.
Precisely. And that difference has huge implications for how we interpret the uncertainty principle.
Okay.
You see, for Heisenberg, the measurement, accuracy, and the spread of the wave function were basically the same thing because of his epistemological view.
Yeah.
But in a valid TCQT, you would actually need to prove a link between measurement accuracy and wave function spread, which isn't a given.
So it's not just about our limited knowledge anymore. It's about something more fundamental about how the universe operates.
Right.
Even if particles do have those definite paths.
Exactly. It shifts the focus from limitations on what we can observe to these inherent limitations on how the universe itself behaves.
Okay.
And this is where the TCQT view really starts to get interesting.
I'm all ears. What makes this TCQT perspective so compelling?
Well, think back to those arrival time measurements that we discussed earlier.
Right.
Standard quantum theory, the one without trajectories, struggles to provide these clear predictions about when exactly a particle will arrive at a detector.
Yeah, it was almost like standard quantum theory just threw up its hands and said, we can't predict that.
Uh-huh. In a way, yeah.
Uh-huh.
But TCQTs offer a totally different perspective
Hmm.
because they actually include particle trajectories. They provide a much more natural and intuitive way to calculate those arrival times.
So even though TCQTs might seem more complex because they introduce these like hidden paths,
Yeah.
they actually simplify certain problems.
Yeah.
It's like taking a detour that ends up being a shortcut.
That's a fantastic analogy. It really highlights a key point. Sometimes a theory that might seem less fundamental because it posits these additional elements like trajectories
Right.
can actually be much more powerful in certain situations.
This is making me wonder if TCQTs can handle arrival times better than standard quantum theory.
Yeah.
Are there other areas where they might also have an advantage? What else can they do that standard quantum theory can't?
That's a great question, and it's something that physicists are actively exploring. TCQTs are a relatively new area of research,
Okay.
But they're already starting to challenge our long-held assumptions about quantum mechanics.
This is all so fascinating. It really
Yeah.
makes you question whether our current understanding of quantum mechanics is like the whole story.
Yeah.
Are there like even deeper levels of reality we haven't even begun to grasp?
It's certainly possible. And that's what makes exploring all these alternative theories so important.
Right.
They push us to think beyond the familiar, to consider new possibilities,
Right.
and to constantly refine our understanding of the universe.
Right.
But even as we delve into all these more complex theories, it's important to remember the core principles that have guided our understanding of quantum mechanics for decades.
Like the uncertainty principle.
Exactly. Even though we've been talking about different interpretations and even challenges to Heisenberg's original ideas,
Yeah.
the uncertainty principle itself remains a cornerstone of quantum theory.
Okay, I'm ready for a little bit of a recap.
Sure.
Can we just revisit what the uncertainty principle actually is
Yeah.
and why it even matters, regardless of whether you believe in particle trajectories or not?
Absolutely. So, at its heart, the uncertainty principle tells us that there are fundamental limits to what we can know about a particle at any given moment.
Okay.
We can't know both its position and its momentum with perfect accuracy.
Right, right.
The more precisely we try to pin down one of those properties,
Yeah.
the less we can know about the other.
And this is true regardless of like the technology we use to measure those properties.
Right.
It's not a limitation of our instruments. It's something deeper.
Exactly. It's this fundamental property of nature. It's baked into the very fabric of reality.
So even though we've been exploring this possibility of particles having these hidden paths,
Yeah.
these trajectories,
Mm.
the uncertainty principle still tells us there's this limit to how much we can predict about their future behavior.
Exactly. And that's where things get really interesting. The uncertainty principle isn't just this theoretical curiosity.
Right.
It has these really profound implications for the way the universe works at the most fundamental level.
Like what?
Well, for one thing, it helps explain why atoms are even stable.
Wait, what? How does the uncertainty principle keep atoms from collapsing?
Remember that electrons in an atom are constantly moving around the nucleus.
Yeah, I remember those diagrams from high school chemistry class.
Aha!
Electrons just whizzing around in these fuzzy orbits.
Right. Now, if we could know both the position and momentum of an electron with perfect accuracy,
Right.
we could, in theory, predict its path exactly.
Okay.
And that would be bad.
Yeah.
It would be catastrophic for the atom. If an electron's path could be predicted with perfect precision, it would eventually just spiral into the nucleus,
Oh, wow.
causing the atom to collapse.
So the uncertainty principle is like a safety net for atoms.
Huh.
It keeps the electrons from crashing into the nucleus.
That's a great way to put it. You see, the uncertainty principle introduces this fundamental fuzziness
Right.
to the electron's position and momentum,
Right.
preventing it from following that predictable path that would lead to a collision with the nucleus.
Wow. So this seemingly abstract principle actually has this very real and essential role in shaping the structure of matter itself.
Absolutely. And that's just one example. The uncertainty principle also has implications for other phenomena, like quantum tunneling, where particles can pass through barriers that would be impossible according to classical physics.
Right.
And it even plays a role in things like the behavior of black holes and the expansion of the universe.
It's amazing how this one principle, which can seem so strange and counterintuitive,
Yeah,
has such far-reaching consequences.
it really does.
It really shows the power of quantum mechanics to explain the universe at its most fundamental level.
Precisely. And as we continue to explore new theories and new interpretations,
Right.
it's important to remember that the uncertainty principle is still a guiding light, helping us navigate the complexities and the mysteries of the quantum world.
Well, on that note, I think we've reached the end of part 2 of our deep dive.
Okay.
But don't worry, there's still more to come. We'll be back soon for the final part of our exploration, where we'll wrap things up and discuss some final thoughts on the uncertainty principle, its implications, and the broader philosophical questions it raises about our understanding of reality itself.
Yeah, sounds good.
All right, see you soon.
See them.
Welcome back to Teolumen Insights. We've been on quite the journey exploring the uncertainty principle,
Yeah, it has been.
from Heisenberg's early arguments
Right.
to these mind-bending implications of trajectory-containing theories.
Yeah, it's been a fascinating discussion for sure.
You know, one thing that's really stuck with me throughout this deep dive is the idea that the uncertainty principle isn't just about what we can know.
Right.
but also about how the universe itself works.
Yeah.
It's not just a limitation on our observations,
Mm-hmm.
but a fundamental property of reality.
Yeah. That's a key insight.
Yeah.
And it really highlights the profound implications of the uncertainty principle. You know, it challenges all our classical intuitions about how things should behave. And it really forces us to embrace this whole new way of thinking about the world.
It's almost like the universe is inherently fuzzy at its core.
Yeah.
We can't pin things down with absolute certainty,
Right.
no matter how hard we try.
That's a great way to put it.
Yeah.
The uncertainty principle introduces this fundamental indeterminacy,
Right.
this kind of inherent randomness into the fabric of reality. And this randomness has some pretty profound consequences, not just for these tiny particles,
Right.
but for the way the entire universe operates.
We talk about how it keeps atoms stable, preventing those electrons from spiraling into the nucleus.
Yeah.
But what other implications does this inherent fuzziness have?
Well, for one thing, it opens up the possibility for phenomena that would be impossible according to classical physics.
Okay.
Take quantum tunneling, for example.
Okay.
Imagine you have a particle that's trapped behind a barrier,
Okay.
like a ball that's stuck in a valley.
Right.
Classically, if the ball doesn't have enough energy to roll over the hill, it will stay trapped there forever.
Right. It needs enough energy to overcome that potential barrier.
Exactly.
Right.
But in the quantum world, things are different. The uncertainty principle allows for this small but non-zero probability that the particle can actually tunnel through the barrier, even if it doesn't have enough energy to go over it. It's as if the ball could suddenly appear on the other side of the hill.
Right.
Like it had dug some secret tunnel through the barrier.
That's wild.
Yeah.
So the uncertainty principle allows for these seemingly impossible events to occur.
Precisely. It introduces this level of unpredictability and spontaneity into the universe
Right.
that classical physics just can't account for. And this unpredictability isn't just theoretical either. It's been experimentally confirmed countless times.
This is blowing my mind.
Uh-huh.
So the uncertainty principle isn't just about, like, setting limits on what we can know.
Right.
It's also about opening up all these possibilities that we never even imagined.
Exactly. It expands the realm of what's possible,
Wow.
introducing this whole new set of rules that govern the behavior of matter and energy at the most fundamental level.
You know, as we're talking about all this, I keep coming back to that idea of different interpretations of quantum mechanics.
Yeah.
We talked about Heisenberg's view,
Right.
where the wave function represents our knowledge, and then the TCQT view,
Right.
where the wave function has this more fundamental role
Yeah.
in the laws of motion. But are there other interpretations out there, other ways of making sense of all this quantum weirdness?
There are. Quantum mechanics is a very fertile ground for different interpretations,
Okay.
each with its own strengths and weaknesses. Some interpretations, like the Copenhagen interpretation, focus on the role of the observer and the act of measurement in collapsing the wave function.
Right.
Others, like the many worlds interpretation, suggest that every quantum measurement splits the universe into multiple parallel realities, each one representing a different outcome of that measurement.
Wow. Parallel universes. That sounds like something straight out of science fiction.
Haha, it does, doesn't it?
Yeah.
But the many worlds interpretation is a serious contender. And it has some pretty intriguing implications for how we understand the nature of reality.
It's mind-boggling to think there might be countless versions of ourselves out there, living out all these different possibilities and all these branching realities.
It definitely stretches the imagination, but that's part of what makes quantum mechanics so fascinating.
Yeah.
It challenges us to think beyond our everyday experiences.
Right.
And to embrace new ways of understanding the universe.
So with all these different interpretations out there, is there one that's considered correct?
Yeah.
Or is it more about just choosing the interpretation that best fits your philosophical outlook?
That's a great question.
Yeah.
And it's one that physicists and philosophers have been debating for decades. The truth is, all of these interpretations are mathematically consistent with the experimental evidence. So in a sense, they're all correct.
Okay.
At least in the sense that they can account for what we observe in the quantum world.
So how do you choose which one to believe?
I think a lot of it comes down to personal preference. to which interpretation feels the most intellectually satisfying,
Hmm.
or the one that best aligns with your worldview.
Right.
Some physicists might prefer interpretations that emphasize the role of the observer,
Okay.
while others might be drawn to those that emphasize the objective reality of the wave function or the existence of multiple worlds.
Right.
It really depends.
It sounds like there's no easy answer.
Yeah.
No single interpretation that will satisfy everybody.
That's the beauty of it. It keeps the conversation going,
Right.
pushing us to explore different perspectives
Yeah.
and to really deepen our understanding of this incredibly rich and mysterious subject.
Well, I think we've covered a lot of ground in this deep dive.
Yeah.
We've explored the historical origins of the uncertainty principle, its implications for the stability of atoms, the possibility of quantum tunneling,
Mm-hmm.
and we even touched upon the mind-bending world of different interpretations of quantum mechanics.
It's been quite a journey.
And throughout all of this,
Yeah.
we've really seen how the uncertainty principle challenges our classical intuitions,
It does.
forces us to embrace a whole new way of thinking about the universe.
Absolutely.
And it opens up all these possibilities that would be unimaginable in a classical world.
That's right.
It's been incredible. Any final thoughts for our listeners?
Yeah, I would just encourage everyone to, embrace the mystery and the wonder of quantum mechanics.
Yeah.
Don't be afraid to dive into those really strange and counterintuitive ideas,
Right.
Just keep asking questions, explore different perspectives,
Yeah.
challenge your own assumptions about how the universe works.
Because even though it can seem so abstract and far removed from our everyday lives,
Yeah,
quantum mechanics is ultimately describing the world around us.
that's right.
I mean, the very atoms that make up our bodies, the light that lets us see, the technology that powers our modern world.
Yeah,
It's all governed by these principles.
that's right.
It's really amazing.
Yeah.
So the next time you hear someone mention the uncertainty principle,
Mm-hmm.
just remember that it's more than just this quirky physics concept.
Right.
It's a window into this profound and endlessly fascinating world of quantum mechanics.
Yeah, well said.
Absolutely.
Okay, well, thanks for joining us.
Yeah, it's been a pleasure.
It's been great.